towards the end of the previous lecture we were discussing about two important terminologies, the spectral radius of convergence and the rate of convergence, and we will be continuing with that. So, let us try to focus a bit on first the spectral radius of convergence. So, as we have seen that if you want to have a very few number of iterations to satisfy convergence, then what should be the spectral radius of convergence. So, just keep in mind that essentially the rate of convergence is related to log of 1 by the spectral radius of convergence. So, if you make a plot of log x versus x, so it will be something like this, right. Now that means if x is 1 by rho, as you have smaller and smaller values of rho, remember that we have the maximum value of rho as 1 to achieve the sufficient condition for convergence. So, that means it is a positive fraction. So, 1 by the positive fraction is a number which is greater than 1. So, smaller the value of rho, larger is this value of x which is say 1 by rho, and larger is log x, right. So, essentially you are dealing with variations towards the right side of x equal to 1 because rho is less than 1. So, as you increase x, your log x increases, and in the limiting case when rho is very small, then log x is very large. That means the rate of convergence is very large. Theoretically, when rho tends to 0, x tends to infinity, so log x also tends to a very large number, and when log x tends to a very large number, that means the rate of convergence is very large. So, you require a very few number of steps to achieve convergence. So, what we can infer from this? We can infer from this is that smaller you keep the spectral radius of convergence, better it is in terms of the rate of convergence. So, to achieve a high rate of convergence, your spectral radius of convergence should be as small as possible. That is the first and foremost thing that we can infer. Now, but how to assess what is the spectral radius of convergence? There are several ways in which you can assess the spectral radius of convergence, but we have to keep in mind is that again to do that in a straightforward way, we need to calculate the eigenvalues of the matrix M, and eigenvalue computation is also expensive. Just like we had seen that the power computation of the matrix M, it is expensive. To get rid of that problem, we came down to the equivalent eigenvalue representation, but equivalent eigenvalue representation, if you want to use that, you need to calculate the eigenvalues of M, that is also expensive. So, we need to go to something which is again equivalent to the eigenvalue representation, but something which is computationally much more straightforward. To do that, we will consider the norm of the matrix M. So, remember that mv is equal to lambda v. Lambda is the eigenvalue of the matrix M. Now, we know that norm of mv is less than equal to norm of M into norm of V, and because mv is equal to lambda v, therefore norm of mv is mod of lambda into norm of v. Right, and from these two it follows that mod of lambda less than equal to norm of m. Since mod of lambda is less than equal to norm of m, maximum of mod of lambda is also less than norm of m, that is the spectral radius of convergence is less than equal to norm of m. So if you can have an estimate of the norm of m, then that is good enough to give you a bound of the spectral radius of convergence, and that can in effect be substituted in place of the eigenvalue representation to get an estimate of the characteristics of convergence. Okay. Now when you say the norm of m, again the question comes that which norm? I mean there we have seen that there can be several types of norms possible. So but some of the limiting norms are, and some of the norms which are easy to calculate are the first norm and the infinity norm, that is the column sum norm and the row sum norm. So a conservative estimate, so an estimate of rho is given by the maximum of the row sum norm and the column sum norm. That is, out of these two types of norms, whatever norm is the maximum one, remember that you have to keep the maximum of the maximum of the lambda, mod lambda maximum out of all lambda i's, that you need to keep less than 1, and norm of m is always greater than that one. Out of all possible norms of m, whatever is the maximum, that if you keep less than 1, that means you are maintaining the, or you are satisfying the sufficient condition for convergence. So you are becoming very conservative. You know that whatever is the norm of m, that is greater than rho. For you it was sufficient to satisfy rho less than equal to 1, but if you satisfy norm of m less than equal to 1, then implicitly you are satisfying rho less than 1 definitely, and out of the two extreme norms, one of those, whatever is the greater one, that you satisfy as less than 1. So that means the other one will automatically be less than 1. So your sufficient condition for convergence boils down to less than or equal to 1. Now let us take an example and see that what can be the norm for the methods that we have learned so far. We will take an example of the Jacobi's method. Why we take the example of the Jacobi's method? Again, for estimating the rate of convergence or any convergence criteria, Jacobi's method will give you a conservative estimate, because Gauss-Seidel is faster than the Jacobi's method. So if it works for Jacobi in an efficient way, you expect that for Gauss-Seidel it will work in a more efficient way. Now for the Jacobi's method, what was m? Minus d inverse L plus u. This was m for the Jacobi's method. Where let us again write what are the entries of L, D and U. So, D is A11, A22. See, eventually the matrix M is a derived matrix. The original matrix which was given to us was the coefficient matrix. Therefore, we should be able to write everything in terms of the entries of the coefficient matrix. So, this is the D and L is A21, A31, A32, then AN1, AN2 in this way. This is L and U is A23, A24 in this way, sorry, we will start with A12, A13 in this way, A1n, then A23, A24 in this way, A2n and so on. Now, D inverse into L plus U. So, D inverse roughly represents what? It remember the diagonal for each row contains only one number. So, D inverse roughly represents the division by the diagonal component of the matrix. For a single scalar number, inverse is 1 by that one. For a matrix where you have more number of entries, it is systematically calculated in a more general way, but the diagonal matrix is a special type of matrix where only diagonal term is there. So, you can write this as L plus U means sum of the off diagonal terms divided by the diagonal term. So, now if you want to calculate the norm of this one, you can calculate either the column sum norm or the row sum norm. Let us consider the row sum norm as an example. So, if you consider the row sum norm, then what will be that? So, sometimes out of the row sum and the column sum norm, the row sum norm is used as a criteria. I mean, there is nothing hard and fast about it, one could use column sum or the max of those two, but usually any one of those is considered. This is just a matter of convention, there is nothing very fundamental about it. It is just a convention that in many cases the row sum norm is used as a representation of the norm of the matrix. So, what will be the row sum norm? For any row we divide by the corresponding diagonal. So, AII for the ith row is the diagonal. So, you divide it by this one, so mod of that one. In the numerator you have summation of mod of Aij where j is not equal to I. And this you expect to be less than equal to 1. To satisfy sufficient condition for convergence. Now, try to relate this with the CFD discretization. In CFD discretization, using the nomenclature that we have considered for the grid layout, this is summation of A n b, that is neighboring A's, divided by summation of AP, mod of both. So, the diagonal represents the grid point P, and the other ones represent, the off diagonal ones represent the neighbors. So, this is like the point P, wherein the other sides of it you have the effect of its neighbors. For a one dimensional system it is a tridiagonal matrix, whereas for a multi-dimensional system it is for a two dimensional system, considering the finite grid considering the finite volume grid layout that we had considered, it is a pentadiagonal matrix. So, you have another 2 diagonals on the 2 sides of it. So, in the 3 dimensional you have another 2, so 7 total diagonals involved. So, it is possible to have several off diagonal or near diagonal terms, but the matrix is generally sparse. These types of matrices are called as sparse matrices, where the coefficients in many of the terms are zeros. So, you have essentially the diagonal coefficients which are non-zero, and you have some of the off diagonal coefficients which are non-zero depending on I mean if it is a tridiagonal system then 3 diagonals, if it is a pentadiagonal system 5 diagonals, but these are not the only terms. So, you have majority of the terms which are away from the diagonal, these are zeros. So, the matrix is densely populated with zeros, and that these types of matrices are called as sparse matrices, and it is particularly important in computational fluid dynamics to understand how to handle these sparse matrices. Sparse matrices are actually very irritating, because if you are trying to represent the matrix as it is, then you are wasting a lot of storage space for storing zeros. We have seen that how cleverly that can be avoided for a tridiagonal matrix by using the tridiagonal matrix algorithm, by converting the storage from a 2 dimensional to a 1 dimensional storage. So, it is important to take care of that in the formulation of the solution procedure. Now, coming back to this effect of the neighbors. So, you have effect of the neighbors as summation of the mod of the neighboring terms divided by the grid point contribution, and that needs to be less than equal to 1 to satisfy the sufficient condition for convergence. Keeping this in view, Scarborough proposed a criterion which is called as Scarborough Criterion for sufficient condition of convergence for the Gauss-Seidel method by taking clue from here, and let us state that. So, Scarborough criteria for sufficient condition for convergence, Scarborough criteria of sufficient condition for convergence in Gauss-Seidel method. It states that you must have summation of mod of A and B by mod of AP that is less than equal to 1 for all equations, and in addition one physically based criterion that is less than 1 for at least one equation. This is a very important consideration which we will try to discuss in more details. So, from the mathematical perspective that we have discussed so far, less than equal to 1 for all equations would have been good enough, because that means that if it is less than equal to 1 for all equations, that means for all rows considered together this is less than equal to 1. So, maximum row sum norm that is less than equal to 1. Now, why less than 1 for at least one equation? So, the criterion says that it is not good enough to satisfy this less than equal to 1, that inequality should be a strict inequality in a sense that it should be less than 1 for at least one of the equations that you are solving for. To understand why it is necessary, let us go back to one of our old examples of one dimensional steady state heat conduction. In a rod with uniform thermal conductivity and the source term equal to 0. The Scarborough criteria is generally, I mean, because people use Gauss-Seidel method more often than the Jacobi's method, it is intended for the Gauss-Seidel method, but with an understanding that its essential conception is based on the understanding, based on the theoretical derivations that we have for the Jacobi's method. Why it is based on the understanding from the Jacobi's method is because the same evaluation is more tedious for the Gauss-Seidel method by virtue of the form of the matrix M, but at the same time because the Gauss-Seidel method is supposed to act in a more efficient way than the Jacobi's method. So, regarding the convergence, whatever you can derive for the Jacobi's method in some conservative way, that can be applied even to the Gauss-Seidel method. Now, let us say that we have a rod of some length L, where we are specifying the heat flux boundary condition at both the sides. And they are equal. Obviously, if you have a one dimensional heat transfer, then if it is at steady state and no heat is generated inside, whatever is the heat flux that has entered from the left face, the same should leave the right face. Now, we number the grid points 1, 2 and 3 and write the corresponding discretized equation. So, for the grid point 2, we have done it a few times earlier. So, let us quickly try to do it. The governing equation is d2t dx2 equal to 0. So, if you use a central difference, then T3 plus T1 minus 2 T2 by, if you call this as delta x, this as delta x by delta x square, that is 0. So, you have T2 is equal to T1 plus T3 by 2. Then for the grid point 1, Q is equal to K into T2 minus T1 by delta x. So, we have T1 is equal to T2 sorry T1 minus T2 by delta x, not with a we can write a minus sign here, minus k into dt dx. So, T1 is equal to T2 plus q delta x by k. Just for symbolic notation, let us call it as C, some constant. Similarly, at the right boundary you have q is equal to k into T2 minus T3 by delta x, that means T3 is equal to T2 minus C. Now, let us try to arrange or organize these equations. So, for the what are our equations? Equation 1, you have T1 is equal to T2 plus C, equation 2 2T2 is equal to T1 plus T3, equation 3 T3 is equal to T2 minus C. So, what is the corresponding summation of sigma summation of mod of A n b by A p for equation 1? How many neighbors are there? One neighbor is there and the corresponding neighboring coefficient is 1 and AP is A1, that is 1. So, 1 by 1 this is equal to 1. This one so 1 plus 1 2 by 2, AP is 2, so that is 1. This one again 1, and we know that this problem is a nil post problem. We have seen by earlier experience that this is a nil post problem, because for such a problem you require to specify at least at one boundary the value of the temperature, because otherwise your specification of the heat flux in equal to heat flux out is already inbuilt with the governing differential equation. It gives no additional, or in the terms of in terminology of mathematics, no linearly independent boundary condition. If you say that this heat flux and this heat flux they are the same and whatever is entering is whatever is leaving. If you say that these two heat fluxes are different, then of course you are violating the basic physics of the problem of the steady state heat transfer. So, what you can see is that this is an nil post problem that we have already figured out. Now, if you see that if you just satisfy the mathematical criteria, all of these are less than equal to 1. 1 is of course less than equal to 1, but none of these are less than 1. So, how can you make it less than 1? Let us say that you specify the value of temperature instead of the heat flux at the left boundary. So, you specify in place of Q given you have T given. If you have T given, let us say T equal to some T star. then this boundary condition will not be the boundary condition for grid point 1. For grid point 1 the boundary condition is T star. For grid point 2 now you can write T2 is equal to, so there is this equation 1 is not pertinent. For grid point 2 you have 2 T2 equal to T1 plus T3, but T1 is not a variable anymore, it is now T star which is known. And for equation 3 whatever it is, it remains. So what now gets modified is for this equation 2 which is new equation 1, what is now mod of sigma of mod of ANB by AP, it is 1 by 2, because now T1 does no more represent a neighbor, in a sense that neighbor is represented conceptually by something which is an unknown. Now you have already substituted a known here, so it is not a coefficient, it is of course physically a neighbor, but mathematically it is no more a coefficient, so mathematically it is no more a neighbor, mathematically the only neighbor is the point 3. So it is 1 by 2 and that means it is less than 1. So now you can see that with redefinition of this problem it satisfies the Scarborough criterion. So the whole understanding what we can derive out of this, that how nicely or beautifully physics follows mathematics or mathematics follows physics. So what we can see here is that there is some criterion which from a mathematician's point of view will come from some linear algebra which does not understand that whether there is one dimensional heat transfer, steady state, unsteady state, heat source is there, whether isothermal or heat flux boundary condition, these are irrelevant for this criterion. This is not a criterion made for solving a heat transfer problem in particular. But if you look at the physics of the problem, you can see that how by ill-posing the physics you disturb this criteria or you violate this criteria, and by well posing the physics you can make the criteria satisfied, and that is very very important. So whenever we solve a problem using the Gauss-Seidel method, say we need to check this criterion, and if this criterion is violated, it most of the times will mean not an error in the discretization but error in the problem formulation or specification itself in terms of giving the appropriate boundary conditions. That is where, see, in CFD most of the times people fail in solving the problem because of the error in correctly giving the boundary condition, because most of the times you are solving the same equation. So either it is a diffusion type of equation, then we will see in our next chapter that it could be a convection diffusion type of equation, and then we will see that it could be the Navier-Stokes equation, the fluid flow equation. So these are some of the equations which hardly get changed as you go from one problem to the other of similar type, but what gets changed from one problem to the other is a correct specification of the boundary condition, and if you violate certain rules or certain physical considerations in specifying the boundary condition, that is where you come up with trouble. And sometimes if you are not physically that intuitive, you may not be able to detect that in the formulation stage, but if you look into the system of algebraic equations that you get at the end and try to assess those mathematically in terms of their consistency, there itself you will be able to detect that there must have been something that has gone wrong in some of your earlier stages of the formulation. Okay. So with this understanding, let us try to work out a couple of examples to illustrate what we have learned so far in terms of the sufficient conditions for convergence for the iterative methods. Consider the following system: 2x1 plus 3x2 plus 10x3 equal to 10, 5x1 minus 2x2 plus 2x3 equal to 5, x1 plus 10x2 plus 5x3 equal to 6. Question is it possible to follow an iterative method say Jacobi iteration for the above system with guaranteed convergence. If yes, what is the estimated number of iterations to achieve 4 decimal accuracy? Now, what is the first thing that we should look for before assessing the method in more details? That whether it satisfies the sufficient condition for convergence. Then the question comes, what is rate of convergence and all those things. So, to satisfy the to assess whether it satisfies the sufficient condition requirement of sufficient condition for convergence, what we have to assess? We have to assess the norm of M. That means essentially we can take as an example a row sum or a column sum norm. So, if we take an example of a row sum norm, what we expect is that summation of aij, where j is not equal to I, mod of that by aii, that is less than 1, less than equal to 1. Of course, less than 1 for at least one equation, but in general less than equal to 1. Now, what does it mean? Now, if you are given two choices, one is a small diagonal coefficient, another is a large diagonal coefficient, which one would you prefer for satisfying this? Large diagonal coefficient. So, you can see that if it is a large diagonal coefficient, then that can overweigh the sum of the magnitude of the off diagonal coefficients, so that this is constrained to be less than 1, right. So, you can see this is very beautiful if you appreciate that it is in a different way, in different words talking about the diagonal dominance. See, when we were studying the elimination method, we were talking about the diagonal dominance, how to reorganize the system of equations to make it diagonally dominant, so that the diagonal element is much more dominant in that particular pivotal row that we were considering for Gaussian elimination with pivoting. Now, you can see that that sense has come back maybe through different mathematical routes, but even for the iteration method, this is essentially what is diagonal dominance, that the diagonal term is dominating over the sum of the magnitude of the off diagonal terms. So, the diagonal term is so dominating that even if you add the magnitude of all the off diagonal terms, that cannot supersede the diagonal term magnitude by itself. So, that is what is absolute dominance of the diagonal term or the diagonal dominance. So, let us try to figure out that what is the situation here. For the first row, for the row 1, what is the case? So, the diagonal, the sum of the off diagonal terms is 2 plus 3 plus 10, that is 13, and the diagonal term is 2. So, straight away this does not satisfy the sufficient condition for convergence. So, as I have said earlier that does not tell you that it will not converge, because maybe you are so lucky that you have already got a clue of the solution by magic or whatever, and you know the solution and you start iterating, that will satisfy the equation automatically. But we are not talking about such fortunate cases. So, we are talking about cases when that will not occur and you are dealing with an arbitrary initial guess, not a guess which is the solution. So, then this will not give you guaranteed convergence, but one may attempt and see that whether a reordering of these equations can do that. So, what is the rationale behind the reordering? You first find out that out of these 3 equations which has the first coefficient highest, that is the second equation has the first coefficient 5 which is the highest, and sum of the off diagonal terms in that case is 2 plus 2 which is 4 which is less than 5. So, let us make this as equation 1. Which has the second coefficient as highest? The third one. So, let us make it equation 2, and the first one let us make it equation 3. If you make it in this way, you see that this criterion is satisfied by all the 3 equations. So, the answer to the first question is yes, it is possible to follow an iterative method for the above system with guaranteed convergence, but after reordering the equations, not in the original order. Then the next part is very straightforward. Let us not move into it in more details, we will just use the formula k greater than m by the rate of convergence. So, for the rate of convergence, that is log 10 1 by rho, and for rho you can take as maximum of either the row sum norm or the column sum norm. Just let us see how to calculate these norms. Of course, we have seen here that how to calculate the norms through non-numerical examples, but just through this numerical example. So, out of all the rows, so the row sum, what will be the row sum norm? For the first row it is, so the first row is corresponding to this equation 1. So, that is 2 plus 2 4 divided by 5, sum of the magnitude of the off diagonal divided by the diagonal. For the second one it is 5 plus 1, that is 6 by 10. For the third one two plus 3, that is 5 by 10. So, out of these maximum is 4 by 5, so that is 0.8. So, the row sum norm is 0.8. Similarly, you can calculate the column sum norm also, and if you want to make a conservative estimate out of, actually if you want to make a conservative estimate of the number of iterations, instead of using the max here you can use the minimum here if you want to be very conservative, because or not, no sorry, if you want to be conservative you want to make rho as large as possible, not the small one, because small rho is better anyway. So, you want to see what is the largest row that you can take. So, out of these two, so you can also consider the column sum norm. So, what is the column sum norm? So, for the first column what is the, so let us just try to organize the columns a bit. So, 5 minus 2 2, that is the first row, second row 1 10 5, third row 2 3 10. So, for the first it is 3 by 5, column 1 it is 3 by 5, column 2 5 by 10, column 3 7 by 10. So, the max is 0.7. So, if you take the maximum of the row sum and the column sum norm, that comes out to be 0.8, and based on that you can calculate k, that is an estimate of the number of iterations to achieve the 4 decimal accuracy. Let us consider one more example. For a linear system of size n, the ith eigenvalue of the Jacobi iteration matrix that is m is equal to minus d inverse L plus u is given by lambda I is equal to cos I pi by n plus 1, where I is equal to 1 2 up to n. It is also known that for sufficiently large values of n, cos pi by n plus 1 is roughly equal to 1 minus pi square by 2 into n plus 1 whole square, is again roughly equal to e to the power of minus pi square by 2 n square. If the size of the coefficient matrix changes from 10 to the power 3 by 10 to the power 3 to 10 to the power 2 by 10 to the power 2, to what proportion would the total number of iterations expected to achieve a desired level of accuracy will decrease. So, this in this problem you are directly given the information on the eigenvalue, and because it is a cosine function, the maximum will be when the argument of the cosine function is a minimum out of all possible ones. So, you can estimate mod lambda max when you consider I equal to 1. So, that is cos pi by n plus 1 magnitude of that. Remember, n is the size of the coefficient matrix, and for the problem it is given that the size of the coefficient matrix in one case is 10 to the power 3 by 10 to the power 3, another case 10 to the power 2 by 10 to the power 2. Both these may be considered to be large enough so that this approximation formula for cos can be used. So, this becomes approximately exponential minus pi square by 2n square. Now, how do you estimate the total number of iterations to achieve a desired level of accuracy? You estimate it through the rate of convergence. So, your k estimation is m by r estimation. Remember that as you are decreasing the size of the coefficient matrix from 10 to the power 3 by 10 to the power 3 to 10 to the power 2 by 10 to the power 2, the accuracy level expectation is not changing to achieve a desired level of accuracy. So, that means the number of iterations k2 by k1 for the two cases will be inversely proportional to r, that is it will become r1 by r2, where r is the rate of convergence. Remember, this is not exactly equal, this is just an estimate. What is the rate of convergence for the first case? So, log 10, so minus log 10 of mod lambda max in case of 1 divided by minus log 10 of mod lambda 2 max, 2 for case 2. So, for case 1 you have to substitute n equal to 10 to the power 3, and for case 2 you have to substitute n equal to 10 to the power 2. In the formula for mod lambda max. If you do that, then you will get this approximately as 10 to the power minus 2. This you can verify later on through calculations, but important thing is the understanding. So, what does it give you? It gives you an estimate of what? It gives you an estimate of the reduced number of calculations that you need to do as you decrease the size of your coefficient matrix to achieve the same accuracy. So, many times one needs to plan for the computational time. So, many times one needs to plan for how many computational hours that you need to devote for solving a problem, and that depends on the size of the matrix, because computational time requirement in an iterative scheme depends on number of iterations. Each iteration will have a fixed number of calculations. So, if you can figure out that what would be the modified number of iterations with a change in the coefficient matrix size, then you can scale the computational time with the size of the coefficient matrix, and this simple understanding allows you to do that. We will our next agenda will be to work out maybe one or two more examples related to the use of the iteration method, and then we will consider the use of the gradient search method for solving the system of algebraic equations. So, that we will take up in the next lecture. Thank you.